Okay, welcome back. So this is the test 4 review. And so I'm just going to go through like two problems in each section and give you a question pull. So for 14.1, I'm looking at WebAssign problems like 18 to 30. So 1 to 17 is basically can you do a double integral, and then the rest were kind of like set up your integral with a change of order and do a sketch and evaluate. Some just have you set it up, like number 22. I think I'm going to look at that one first. So they want you to sketch the region kind of designated by the integral and then change the order of integration. They don't ask you to actually integrate. So I'll specify that on the question, so make sure you're reading the questions. But anyways, given the integral 1 to 4 and then 0 to ln y of f of xy dx dy. So let's get a picture of what it looks like. Remember that the inner limits kind of tell you, so in this case the first inner part is dx, so it's going from x equals 0 to x equals ln y. I'm going to rewrite that because I'm not used to plotting x equals ln y. So you can exponentiate both sides, and of course then y equals e to the x. So x equals 0 is just the y-axis, and then y equals e to the x looks like this. And then on the y-axis I'm going from 1 to 4. So of course this point right here, if you plug 0 in for x, you get 1, so this is the point 1, 0. So on the y-axis, note it's going from y equals 1 to y equals 4. So 1 to 4 up here. So the region we're worried about, x equals 0 is the y-axis, to x equals ln y, which is this curve here. So it's, and then y equals 1 to 4. So it's this region that we're worried about integrating over top of. Okay. All right, so now I need to change the order of integration. So I would ask you that you have to do a little sketch if I call you upon to do so. And then we'll have f of xy dy now dx. So it's going to go y equal what to y equals what. So this time y equals this curve, which we just found is e to the x, to y equals this curve, which is y equals 4. And on the x-axis, I'm going to go from, looks like 0 to whatever this point is on the x-axis, right? So that point there is going to be what? So x will equal ln of 4, right? So it's going to be, the ordered pair is ln 4, comma 4. Okay, so on the x-axis, I'm going from 0 to ln 4, and there's my other integral. Okay, let's look at 26. So this time you are sketching the thing, changing the order, and then integrating. Okay, so it's one of the nasty ones where it has a sum of integrals to describe the region. So 0 to 2, 0 to x, dy dx, plus 2 to the 4, and then 0 to 4 minus x, dy dx. So I want to sketch it, change order, and then evaluate. Sketch, change order, and then finally evaluate. Okay, so sketching the thing, y equals 0 to y equals x, so on that inner integral. Y equals 0 is the x-axis, y equals x is this diagonal line, and then from 0 to 2 on the x-axis, so maybe about right here, and it's this region. And then the next integral goes from 2 to the 4 on the x-axis, but the curves y equals 0 is the x-axis to y equals 4 minus x. Okay, so if this is 2, this point right here will be 2, 2. And then 4 minus x has y-intercept at 4, and that goes down 1 over 1, right? Down 1 over 1. So it's going to hit right here, down 1 over 1, down 1 over 1. So it's going to have an x-intercept at 4. It's going to look like this. So it's from 2 to the 4 on the x-axis, so it becomes this region right here. I want to change the order of integration then to dx dy. So I want to go from x equals this curve to x equals this curve, right? And then on the y-axis, I'm going to go from 0 to 2. So I already can kind of fill in the outer integral part. But I need formulas for those two curves. So the first curve, the first blue curve, is y equals x, which I could just write as x equals y. So I'm going from x equals y to, and then this other curve is given in the other integral as 4 minus x equals y. So I can rewrite it as x equals 4 minus y. Okay, so the upper integral the upper limit on the inner integral is 4 minus y, and then I'm going to go ahead and evaluate that thing. So I have an integral of, first with respect to x, I get an x, and then I have to evaluate that dy. Of course, that'll be 4 minus y dy, and that's 4 minus 2y dy, and then integrate with respect to y, so that's 4y minus 2y squared over 2 is just y squared, evaluated from 0 to 2, and we have then 8 minus 4 minus 0, so at the end of the day you're just getting 4 for your integral. Okay, so that's 14.1 stuff, changing order of integration, sketching regions, all that great stuff. Okay, so let's go to 4.2 now. And here we go, 14.2. So we're finding volumes, I guess, in this section. We're working problems 2 to 17. And again, it's kind of the same stuff, except like in the previous problems, you really wouldn't have an integrand, right? Now we're going to have something inside these double integrals, and it'll represent basically a volume. So let's look at number 9. They want us to set up the orders, set up both orders, sketch, and evaluate. Okay. And they're giving us a double integral over this region R of y all over 1 plus x squared dA. And the region is bounded by the curves y equals 0, y equals square root x, and then x equals 25. So let's get a graph. Y equals 0 is the x-axis, y equals square root x is this curve here, and then x equals 25 is a vertical line at 25. We may need this point, so let's figure that out. That'll be 25 comma 5. This is the region we're integrating over. Okay, so we need both orders. So double integral. I guess we'll do y all over 1 plus x squared. Let's do dy dx first. So dy, y equals 0 to y equals square root x. Okay. So 0 to square root x, and then on the x-axis we're going from 0 to 25, right? Excuse me. Then on the other integral, the other variation, you're going from x equals this curve to x equals this curve. So the upper curve is 25. The lower curve I get from the y equals square root x. So x will just equal y squared, so y squared to 25, and then on the y-axis I'm going from 0 to this y coordinate 5. Okay, 0 to 5. And then of course we have our integrand y over 1 plus x squared dx dy. Okay. If I integrate with respect to x first, it looks like I'm going to have an arctan to deal with, and I'd rather not. So what I'm going to do is the dy dx first. Okay, so I'm going to choose this integral, so please choose wisely, otherwise these integrals can be kind of nasty. So with respect to y, I'm going to get y squared over 2. So I get y squared, I can factor out the 1/2 then, and 1 plus x squared, evaluated from 0 to square root x dx, plugging in the square root x and for y squared, you just get x over 1 plus x squared minus 0. And then that thing we just use a u sub on, so u is 1 plus x squared, and then du is 2x dx. So dx is du over 2x. So I'm going to end up with 1/4 really, because there'll be another factor of 1/2 to pull out. The x's will cancel, and I'll just have the integral of 1 all over u du. Right? Then I'll have 1/4 ln, absolute value, but you don't need it, so 1 plus x squared only from 0 to 25, and then evaluate. So that's going to be 1/4 ln of 25 squared plus 1, whatever the heck that is, and then minus 1/4 ln of 1, which is 0. Okay, so you could leave your answer like that if you wanted to. Anyways, we used this sort of double integrals with an integrand inside to figure out volumes of given regions. So like number 11, I could ask you to do something like that. We have the region given by a picture, so I'll try to maybe put a picture in there, maybe not. See how I feel about that. Anyways, here's 8. I have y equals x in the xy plane, and then y equals 4 in the xy plane, and then there's this plane over top of it enclosing this region, and we want to find, well, I guess I screwed that up. It's not quite. So there's another line kind of like right here all the way up to, I think it's 4, and then this goes down like this. So it's z equals 8 minus x minus y, and then there's kind of like this region. Okay, so how the heck do I do this? Well, you're going to put the plane that's cutting through the space in the integrand. So you have the 8 minus x minus y in here, and then you're going to go dy dx probably. So you can redraw this in the xy plane and kind of think about the region, how you're going to set up your integrals. So you have a y equals x and then a y equals 4, and you're integrating over this region. So you're integrating from y equals x to y equals 4. So you have x and then 4. And then on the x-axis, it looks like you're going from 0. This point, because it's on the coordinate on the line y equals x, is going to be 4, 4. Right? So you're on the x-axis, you're integrating from 0 to 4. So 0 to 4 here. And then it's just chug away, right? So integral with respect to y, 8y minus xy minus y squared over 2 from x to 4 dx. So that will be, put in the 4 first, so you get 32 minus 4x minus 16 over 2 is 8 minus 8x minus x squared minus x squared over 2 dx, of course. Then we are subtracting some terms here, right? So 32 minus 8 is going to be whatever it is. So 6, 24. There's negative 4x and negative 8x is negative 12x. And then there's this 2x squared over 2 plus x squared over 2. So it's plus 3x squared over 2 with respect to x. So that's going to be 24 x minus 12x squared over 2 is 6x squared plus 3x cubed over 3 times 2, which is x cubed over 2. And then we need to value it from 0 to 4, I think we said. Okay, so putting in 4, you get some nasty stuff. I'd probably just put it in my calculator at this point, but it's going to be 24 times 4 minus 6 times 16 plus, 16 times 2 basically, so 32, and that'll equal 32. Okay, great. 14.3, we get into polar coordinates, so doing polar conversions to evaluate curves. So let's look at 14.3. 14.3. And in particular, I'm looking at problems like 6 to 15. Let's look at number 10. Okay, so you got to convert to polar, but in order to do that, you kind of have to have a picture, right? So here we go. 0 is 6x minus x squared, xy, dy, dx. Okay. Right. So I need to figure out what I'm dealing with. I'm going from y equals 0 to y equals the square root of 6x minus x squared. So if you square both sides, you get y squared equals 6x minus x squared. Set it equal to 0, so you get x squared minus 6x. Complete the square, so plus 6 over 2 is 3. 3 squared is 9. Immediately subtract 9 plus y squared equals 0. Factor x minus 3 squared plus y squared equals 9. So get a shifted circle with center at 3, 0 and a radius of 3. So 1, 2, 3, 0, 1, 2, 3 for the radius, 1, 2, 3, 1, 2, 3, and it looks like this then. And you should be able to get the equation, the polar equation for a shifted circle. So it's always just r equals 2 times the radius times cosine theta. So remember, there's kind of like 3 main formulas you have to be able to do for the test. The basic circle. So if this had radius 3, your equation would be r equals 3. Then there's the kind of the case we're just looking at. This would be r equals 6 cosine theta if the radius was 3. And then there's the other kind of version where your circle is like this. And in that case, r would equal basically just 6 sine theta. Okay, so you should be able to graph or convert any of those types of forms. Those are the basic ones. I'm not worried about rose petals or renaissance or anything crazy. So anyways, doing your polar conversion then, for the r part of the integral, you're going from r equals 0 to r equals 6 cosine theta. 0 to 6 cosine theta. Just by the way, when you're dealing with these shifted circles, they will be traced out going from 0 to pi. So that's always kind of like the freshman mistake. You forget and put 0 to 2 pi, right? So those are 0 to pi. The regular one is 0 to 2 pi. So this non-shifted circle is traced out from 0 to 2 pi. But anyways, there's other issues on the x-axis. So if you look at the original integral, we're going from y equals 0 to y equals the upper hemisphere, basically, of the circle. So in actuality, this is the region we're dealing with. It's not the whole circle. And so when you think about the tracing with regards to theta, it's going to trace out from 0 to not pi, but pi over 2, because it's only half that circle. The full circle would be traced out from 0 to pi. Half the circle would be traced out from 0 to pi over 2. Okay, so be careful. Then we want to do conversions on xy. So x is r cosine theta, y is r sine theta, and then we have r dr d theta. Right, and then we can rewrite that as r cubed cosine theta sine theta dr d theta, and then we can go ahead and rewrite that baloney. Integrate, right? So have r to the 4th over 4 cosine theta sine theta evaluated from 0 to 6 cosine theta d theta. So it'll be the integral of something ridiculous, right? So 6 to the 4th all over 4 And then we have cosine to the fourth times another factor of cosine will give you cosine to the fifth theta, sine theta d theta. Then you want to do a u sub for cosine. So our du will be negative sine theta d theta. So there's a negative floating about, so I'm going to move the negative out to the front, and then do my u sub for u to the fifth now du, and then integrate that. So negative 6 to the fourth over 4 times u to the 6 over 6. Evaluate it. That'll be negative 6 cubed over 4 times back subbing. For u, we get cosine to the 6th theta, and then I need to evaluate from 0 to pi over 2. Okay, so negative 6 cubed all over 4 times cosine of pi over 2 is just 0, and then minus cosine of 0 is 1. 1 to the 6 is 1. So you end up with 6 cubed all over 4. Or the 24. Well, I got rid of that one. So whatever the heck that is, right? 6. I think it's 54. Okay, let me make sure. Heaven forbid I do some arithmetic, without going to my calculator. Screw it up. Let's move this out of the way. Get the calculator. 6 to the third divided by 4 is 54 grand. Okay, so that kind of stuff. Let's move on to 14.4. And if you remember, 14.4 was doing centers of mass, so centroids and stuff like that. I'm not going to include physics stuff on my math tests. 14.5, I'm looking at questions like 1 to 10. This was on surface area, which will become important for us. So let me cruise on over the 14.5, and the sort of formula du jour for surface area, you're integrating over some region of the integral of the square root of 1 plus fx squared plus fy squared. So you need that memorized, of course. Anyways, 14.5, and you need all your conversion formulas memorized, so hopefully you got that done. 14.5, let's look at number, let's see what I have here. Let's try number 5, I guess. So number 5, we have f of xy equals 3 plus 6x to the 3 halves, and we're integrating over this rectangle, 0, 0, 0, 2, 6, 2, and then 6, 0. Okay, so you could draw a little picture if that helps. 0, 0, 0, 2, 6, 0, and then 2, 6, or 6, 2. Sorry. Okay. So in order to pull this off, I need f with respect to x. That's going to be 6 times 3 halves x to the 1 half, which is 9x to the 1 half. I need f with respect to y. That, of course, is 0. And so my double integral will be integrating from, let's do dy first. So y equals 0 to y equals 2. And then x equals 0 to x equals 6. Our integrand will be the square root of 1 plus 81x plus 0. And then we decided dy dx. Probably going to need to do a u sub on this character. U would be 1 plus 81x. So du is 81 dx. So you get a factor of 1 over 81 popping out. What else? Okay, so I need to integrate that thing then. What is it? It's the integral of the square root of u with respect to u, and then dx, I believe. Well, I'm doing, wait a second, I'm getting carried away, right? I have to do dy first. Sorry. So eventually we're going to do that u sub. Let me just put it in parentheses for now. what do I need to do? I need to integrate with respect to y. So it's going to be y square root of 1 plus 81x evaluated from 0 to 2 dx. So I'll have 2 minus 0. 2 times the square root of 1 plus 81x minus 0, which will just be 2 times the square root of 1 plus 81x. So I'm going to factor out the 2. The double integral of the square root of 1 plus 81. Whoops, not double integral anymore. We integrated once. So square root 1 plus 81x dx. And then I'm going to do my u sub on this. Okay. So I'll end up with 2 all over when all is said and done, 81 times the integral of u to the 1/2 du. Okay, so it'll be 2 all over 81 times u to the 3/2 now times 2/3. Back subbing 4 all over 273 times 1 plus 81x to the 3/2 from 0 to 6. And then we get 4 all over 273 times 1 plus 486 is 487 to the 3/2 minus 1 plus 0 to the 3/2 just 1. Okay, so expect that kind of stuff. Some of these you have to actually convert, I think, the polar coordinates to get the job done. But let's move on to 14.6. And 14.6, we were doing triple integrals, looking at 6 to 11. I'm not going to put any of the crazy ones on there where you have to figure out all 6 order of integration. Those ones were kind of nasty. I'm not going to be that kind of teacher. So anyways, basically you're looking for volume, mainly in this 14.6 using triple integrals. So let's try number 6. Or actually, yeah, sure. Let's try number 6 and go from there. And this one, they just want you to set up the integral. So it's a solid in the first octant bounded by the coordinate plane, and z equals 6 minus x minus y. So let's get a picture of that plane going through the first quadrant, or the first octant, sorry. So if you let x and y equal 0, you get z is 6. If you let z and y be 0, you get x equals 6. And if you let x and z be 0, you get y equals 6. Okay. So you get this picture here. And I want to find the volume underneath this surface. So in my triple integral on the inside, and I'll go dz, dy, dx. On the inside, you will go from the surface z equals 0 to the surface z equals 6 minus x minus y. And then you kind of go down a dimension, right? So you start thinking now, instead of the xyz space, you think in the xy plane. So xy plane, we have this region that we're integrating over in that first octant. So it looks like y equals 0 to y equals whatever this line is, right? So that would be y equals, the slope is probably going to be negative, right? -1, so negative x plus 6. If you don't know the slope, you can just use the points, right? 0, 6, and 6, 0. The slope will be y2 minus y1 all over x2 minus x1, so you get -6 over 6, and yeah, in fact, it's -1. Okay. So I want to go from y equals 0 to y equals negative x plus 6, and then I want to go from x equals 0 to x equals 6, and that would just set it up for me. Let's look at one more that's a little more complicated. So number 9. Use triple integral to find the volume of the solid bounded by the graphs. So our graphs are z equals 6x squared, y equals 3 minus 3x, and it's in the first octant. Okay, so in the zx plane, it's just going to be a parabola, so you can kind of draw that in. Here's z, here's x. So it's going to kind of look like this. in the ZX plane, and then it's going to carry on that way in the Y direction. So kind of trying to, it's like the side of a boat, you know. But anyways, it looks something like that. And the plane y equals z, y equals 3 minus 3x. Well, where is that? That has a y-intercept at 3. So 1, 2, 3-ish. And then down 3 over 3. So it's going to be like this. And so we're kind of looking for the region underneath this parabola. Maybe if I put it in a different color, that would help. Okay, like underneath in there. So the top is really this parabola part, and the bottom is just the xy plane, so z equals 0. And then we could consider what's going on in the xy plane that we're integrating over top of. And of course, it has a x-intercept of 3, slope down 1, 2, 3 over 1, 2, 3. So there's that picture. So our integral is going to become, doing a triple integral now, and I want dz first, then dy dx. So z is going from 0 to the 6x squared, and then y is going from 0 to 3 minus 3x, and then x is going from 0 to 3. Okay, right, so then go ahead and integrate. So we get the double integral of z dy dx. So that's going to be the double integral of 6x squared dy dx. That's going to be 6x squared y evaluated dx. That's going to be 6x squared times 3 minus 3x dx, and then minus 0. That's going to be the integral of 18x squared minus 18x cubed dx. It's going to be 6x cubed minus 9 halves x to the 4th from 0 to 3. And then that's going to be, you know, oops, is it 0 to 3? The slope is down 3 over 1, not down 3 over 3. Oh, sorry. It's this curve. Always making mistakes, I swear. So it's from 0 to 1. I was starting to think this, so that doesn't affect things too much, just changes that upper limit. 0 to 1, so I have 6 minus 9 halves minus 0. So 12 halves minus 9 halves, which is 3 halves. Okay. Next section then, I'm thinking 14.7, and those were triple integrals and cylindrical coordinates and spherical coordinates. Of course, I'm not doing any spherical coordinates on my test. I'll just do plainly the spherical. Let's look at 14.7. Where are you? So this is now 14.7. Questions 6 to 8 are fair game. So not a lot of questions to choose from, really. Most of them are just, do you know how to evaluate triple integrals? But these last ones were kind of a little more challenging. So let me try number 8. And you know, I'm not going to put anything crazy on the test. This problem does get kind of crazy, though. I'll just warn you. But anyways, we got the solid bounded by r squared plus z squared equals 25, and r equals 5 cosine theta. Okay, so this thing right here, if you do a conversion on r squared, it's x squared plus y squared plus z squared equals 25. That's a sphere. And then this guy right here is one of our friendly shifted circles with radius 2.5. Okay, so if you kind of put this into 3 dimensions, what you're dealing with then is kind of a circle here. going out to 5 on your sphere. And then if you let z vary for this guy right here, the r equals 5 cosine theta, that becomes a cylinder. So it's going up and then kind of cutting through our sphere, okay, more or less. So it's going to come up and kind of slice through the sphere right about like that. And you are tasked with kind of finding the volume inside the cylinder, inside the cylinder and the sphere. Okay, the solid bounded by the graphs of the sphere and the cylinder. So this is only half the picture. This really, it goes down as well. So the way I have it set up right now, I'm going to have to multiply my integral by 2 if I do this like triple integral. And I'm going to go the polar I'm in polar coordinates already. So I'm going from z equals 0, the xy plane, to z equals, and I'm going to take this character, mainly this character, right, and then solve for z. So I'll end up with z equals the square root of 25 minus r squared. So z equals 0 to the square root 25 minus r squared. And then I'm going to go from on the r, with respect to r, the region I'm integrating over is the 0 to 5 cosine theta. And then, of course, that's from 0 to pi to get that thing. And then it's just r dz, dr, d theta. Okay, so nasty integral here. Let me give myself some more room so I don't feel like I have to smush everything in and skip steps. So 2 integral zr dr d theta. That will be 2 integral r times the square root of 25 minus r squared dr d theta. You're going to probably have to do a u sub on there, so that's 25 minus r squared, so that would be du is negative 2r dr. So I'm going to end up with a negative 1/2 that I pull out. That'll leave me with a negative 1, and then I have double integral of u to the 1/2 du d theta, and then negative integral. Well, I'm going to integrate, so I don't need the integral anymore. So u to the 3/2 times 2/3. I'll pop the 2/3 out, evaluate eventually. So I have negative 2/3 integral, back subbing 25 minus r squared to the 3/2 and evaluating from 0 to 5 cosine theta d theta. And then let's see what we get now. So we got negative 2/3 integral 25 minus 25 cosine squared theta to the 3/2. And I'm going to split this, eventually split it in the two integrals, but minus 0 in there. So it would be 25 to the 3/2 d theta. Yeah, and I'm going to split it in the two integrals now. So I have negative 2/3 integral 25 minus 25 cosine squared. That's the same as 25 times 1 minus cosine squared theta. And that's the same as 25 times sine squared theta. And then when you raise that thing to the 3/2 power, 25 to the 3/2 is going to be 25 to the 1/2 cubed. 25 to the 1/2 is 5. 5 cubed is 125. And then sine squared to the 3/2 will be sine to the 6/2, which is sine cubed theta. So that whole thing then, once I raise it to the 3/2 power, will become 125 sine cubed theta. And then I'm going to cut this into two integrals, distributing the negative 2/3. I'll have 2/3 times, again, 125. The integral of this d theta, and then for the first integral I'm going to have to do some trig manipulation. So this will be let me factor out the 125. Okay, so I got 250 out here, and sine cubed is the same as sine theta times sine squared theta. d theta. The second integral will be 250 all over 3 times theta from 0 to whatever, pi. Then this will be negative 250 all over 3. I'm going to rewrite sine squared as 1 minus cosine squared. Then I have to do a u sub on that. Plus 250 over 3 evaluating it would be pi minus 0 is just pi. So that part's done. Here I'm doing a u sub on that first integral for cosine theta. So du will be negative sine theta. I can factor out a negative and I get 250 thirds integral 1 minus u squared du plus 250 over 3 pi. This is 250 over 3 times u minus u cubed over 3 plus 250 over 3 pi. And then 250 over 3 times back subbing cosine theta minus cosine, I have to evaluate this part, cosine cubed theta over 3, evaluated from 0 to pi, plus the 250 over 3 pi. Then you can evaluate this guy. You want to be careful though. 250 over 3. Cosine of pi is negative 1, minus cosine again of pi is negative 1. Negative 1 cubed is still negative 1. So get negative 1 over 3. Then minus, plugging in 0, you don't get 0, right? Cosine of 0 is 1, minus, again, 1/3, plus 250 over 3 pi. This will be 250 over 3 times all of this junk, right? So that would be negative 2 plus 2/3, which is negative 6/3 plus 2/3, which is negative 4/3, plus 250 thirds over 2 times pi, which will equal a negative 1,000 ninths plus 250 over 3 pi. Okay. All right. Was that the answer? Yeah. Okay. Last but not least, then the Jacobian problems. So I'm most likely to just give you one of the ones where you have to do it all yourself. 14.8. There's only like 3 of them in the homework, so 2 of them. No, 3. 9 to 11. So let's go over to 14.8 and take a look-see at number 11. Okay, so we have f of xy equaling the square root of x minus y times x plus 2y. Our region is 0, 0, 1, 1, 3, 0, 2, negative 1. Okay. So I'm going to go ahead and get my kind of picture and then my equations. So 0, 0, 1, 1, 3, 0, 1, 2, 3, 0, and then 1, 2, negative 1. Okay, so my first line, I'll do this one right here. 1, 1. That's clearly just y equals x. So I'll have an x minus y, and usually I just let that equal my v. So my v is x minus y, and so I'm starting at v equals 0. Then the next guy, the one that's parallel to it, I'll have 2, negative 1, and then 3, 0. It has the same slope, just visually you can tell. So it'll be y equals x plus b, 1x plus b. Then you can plug in like 3, 0 to find out the intercept. So y is 0, x is 3 plus b, so b is negative 3, so it's y equals x minus 3. So x minus y equals 3, so v equals 3. The next one then, let's do this guy, this line 3, 0, 0 to 2, negative 1. The slope in that case is negative 1 all over 2 minus 0, so negative 1/2, which is annoying. Y equals negative 1/2 x. Let's rewrite this as 2y equals negative x. So we'll have x plus 2y equaling 0, and I'll let my u equal this plus version, x plus 2y. So we're going to start at u equals 0. Then finally the fourth line, 1, 1, and then 3, 0. You know the slope already is going to be negative 1/2. And then y equals negative 1/2. So I'm going to plug in, my x and y. Y is 0, x is 3, and then plus b. So b is going to be negative 3 or positive 3/2. So our equation will be y equals negative 1/2 x plus 3/2. Multiply everything by 2, you get 2y equals negative x plus 3. So x plus 2y equals 3, and so u equals 3. Okay. I need my Jacobian, so I need to rewrite the x and y formulas, get some x and y formulas in terms of u's and v's. So note u is x plus 2y, v is x minus y. So if you go u minus v, that's going to be, the x's will cancel and you get 2y plus y will be 3y, so y is equal to u minus v over 3. And then if you go u plus 2v, I believe, you'll get 3x, and then you got x equals u plus 2v all over 3. And all I'm doing is kind of just adding or subtracting column-wise to figure those formulas. All right. Okay, so for the Jacobian then, from the x part with respect to u is 1/3, with respect to v it's 2/3. For the y part with respect to u it's 1/3, with respect to v it's negative 1/3. So you get negative 1/9 minus 2/9, which is negative 3/9, which is negative 1/3, which tells me I need a factor of 1/3 for my Jacobian. Okay, finally I can go to my integral. So I have 1/3, I'm going to totally factor out. Double integral 0 to 3 on both. Not much to screw up there. Note that f of x, y in terms of u's and v's is just going to be the square root of u times v, the way I've set it up. So I was clever enough to work that out. So I have u to the 1/2, v to the 1/2, and you could go dv du. It's not going to make a difference. So I'll just go du dv. So it's going to be 1/3 integral of u now to the 3/2 times 2/3 v to the 1/2, evaluate du, or sorry, dv now on the outside. Plug in 0 to 3, so you're going to get 2/9, and then integral of 3 to the 3/2 v to the 1/2 dv. You could factor out the 3 to the 3/2, so you get 2/9 times 3 to the 3/2. The integral of v to the 1/2 will give you v to the, I want to write a u desperately apparently, v to the 3/2 times another factor of 2/3, evaluated from 0 to 3. So this would be 4/27 times 3 to the 3/2 times 3 to the 3/2 minus 0. And then that would be 4/27 times 3 to the 6/2, which is 3. 27 is just 3 cubes, so these guys cancel and you get 4. Okay. Alright, so that will do it. I'll try not to put anything too crazy on the test, like this guy right here was just nuts, number 8. I mean, it's easy, it's just time consuming, and it leaves the door open for millions of tiny little errors, you know. And I don't like to have to sit there and grade people's little mistakes. So I'll try to make it reasonable, but that should give you a pretty good idea what's on the test. As usual, thank you for watching, and I'll see you next time.